All right. So we've been talking about organic chemistry here, and we've been talking about specifically the last couple times aldehydes, their ketones. Last time we got into some carboxylic acids today. I know there was a question about sort of drawing some of these things online on the homework. I did want to kind of go over a couple of reactions with aldehydes and ketones kind of first, and then we'll take a look at maybe the drawing there in the online homework. And then obviously, if you have any other questions, we'll take care of those as well. So we don't run out too much time here, I'm going to just kind of touch upon some reactions that I talked about with the other half of the class there. They're in their discussion. Again, that way everybody's obviously on the same page. And like I said, if you do have any other questions, and I'll be more than happy to answer those after this. And like I said, we'll take a look at the drawing things, see if we can kind of figure out kind of how to do that, or maybe answer some questions and stuff like that. All right, so that's sort of the game plan here. So let us get into a little bit about some other types of reactions involving aldehydes and ketones. As we talked about last time, our aldehydes and ketones. Obviously, aldehydes, as we've talked about, have this as our functional group, ketones being our 3-carbon run. And as we talked about today, essentially they are produced really from oxidations of alcohols. So our primary alcohol, all this part out like so. So if we took our primary alcohol, such as this guy here, and send it through an oxidation reaction, remembering it is going to remove 2 H's and make our aldehyde there by double bonding between the oxygen and the carbon there, and leaving us 1 hydrogen, which gives us obviously our aldehyde. As we talked about as well, can continue on here through one more oxidation step, which is where those kind of Benedict tests and such are helpful. As this gets oxidized, it's going to actually gain an oxygen in the process right there, and making what we know now, as obviously we talked about today, our carboxylic acid, that being propanoic acid, as it has 3 carbons attached to it, this being propanal, being our aldehyde, coming from 1 propanol, which is our primary alcohol, right? Again, they're all really related to each other. Again, this being propanoic acid. And obviously our secondary alcohol is where we do yield our ketone. That would be an H. Again, going through the oxidation step here, we're going to take off a hydrogen from the oxygen, hydrogen from the carbon. That's going to yield us our H2 and our double bond that's going to occur now between the carbon and the oxygen, leaving us this guy here, this being 1, 2, 3, 4. So butanone, right, which is our ketone, coming from 2 butanol, which is our secondary alcohol. Again, remember, kind of lacking a hydrogen here, so we'll not go through again another oxidation step. So as we talked about, that's where our Benedict test can kind of tell us this has happened. Well, obviously we wouldn't see that occurring here with our ketone. So one thing I did want to sort of also talk about is we did talk about that, going the opposite way here is the reduction reaction at each of these steps. And I just want to kind of go through sort of what happens when we kind of do the reduction reaction, basically taking us back from the aldehyde to the primary alcohol, or from the ketone back to the secondary alcohol. So let's just say we started with that guy. We got there 3 carbons, looks like. So let's say we did actually start with our aldehyde in this case. And we're going to do basically a reduction reaction, which basically means we're going to add H2 to it. And basically it adds 2 hydrogens. It works very much like what we talked about with alkenes, where we have a double bond and we add hydrogen to it. Basically what we do is we make this double bond into a single bond, and obviously we put a hydrogen on each of the carbons. The exact same thing happens when we do the reduction reaction going backwards. It's all about right here, except obviously it is not 2 carbons, but it is a carbon oxygen double bond. So the exact same thing happens. Everything stays the same, except we will make this double bond into a single bond to make room for each of these hydrogens to come in. So much like we've done before, we would just draw it like normal. We'll do our single bond here and leave that like it is. At this point, by making that single bond on the carbon oxygen, that gives us room to add each of these hydrogens in. And just like we did here, the hydrogens will go to separate carbons. Hydrogens here, one would go to the oxygen and one would go to the hydrogen. And that is, again, how we regenerate from the oxidation part, doing a reduction reaction, which means we added H2 to get back our alcohol. So this is sort of the opposite of the other reaction, our aldehyde going back to our primary alcohol. Question on that reaction there. And the same exact reaction happens with our ketone. So we'll just steal the same ketone we had over here. Looks like we got 4 carbons on that guy. So we started with our 4 carbon ketone here. And again, we add H2, which basically implies that we're going through a reduction reaction. It's really the exact same process is occurring here. Nothing else changes. We're going to focus in right there on the double bond of the carbonyl group. And we're going to do the same thing. We're going to turn it into a single bond. So we would draw this guy exactly the same. And now by making that into a single bond, we have now opened up for our H2, which is like a symmetrical addition, a place for one hydrogen and a place for another. I'll just slap a different color on this. So again, just like in the double bonded carbon, one goes to one goes to the other. And now we got back from our ketone here, our secondary alcohol. So remember that basically the sort of reverse reaction for an oxidation reaction is a reduction reaction. And in most cases, the reduction reaction means that we're basically adding H2, our 2 hydrogens. And really, it works pretty much identical to what we saw with our alkenes. Only difference here is it's a carbon-oxygen double bond. But the same idea and process occurs. We want to make it into a single bond so we have room. And then we just give one element a hydrogen. The other element in the double bond gets the other hydrogen. Any question on the reduction reactions here? Which takes us back to our alcohols. Okay, then speaking of alcohols and sort of aldehydes and ketones, I did also want to talk about 2 sort of sets of reactions that occur with an aldehyde and an alcohol, and basically a ketone and an alcohol, and a couple of things that we sort of yield as a result of it. So we'll start with actually the aldehyde. So if we start with an aldehyde, and we'll just steal the same one I think we just did, which was maybe this one or something like that. So we have our aldehyde, and if we add to it an alcohol, I'm just going to kind of draw it this way first. And it doesn't really matter. Give it a few carbons. Why not? Okay. So in this particular case, we have an aldehyde and an alcohol. And pretty much when you add an aldehyde and an alcohol together, you get essentially the same reaction we just saw. We're going to have an addition reaction that occurs, surprisingly enough, in that exact same spot. And just like what we had previously, we need to kind of make that double bond into a single bond to make room for what's going to be added in. Now, earlier we added in 2 hydrogens, so it wasn't like you could kind of mess it up. You put a hydrogen on one, hydrogen on the other. There's not a lot of places to maybe go wrong there. When we add an alcohol to an aldehyde, it does add in a different way. And when we look at the alcohol, there's really 2 parts of it that we'll add. So we'll just kind of color code it here. So one part that gets added is a hydrogen. So hydrogen is one part that gets added, kind of like when we had 2 hydrogens. The other part that gets added is basically this oxygen group here, this oxygen carbon group right here. So the alcohol gets broken up into these 2 parts, and that is what's going to basically be added into our aldehyde. So let's see where everybody ends up. So first off, we could start like normal. We're pretty much going to draw this aldehyde exactly the way it is. The only difference is, again, we're going to make room for everybody. So we're going to turn that double bond into a single bond. So we'll do this deal here. This. And again, turning my double bond into a single bond. And we obviously still have the H that's there. So where everybody ends up is kind of like before. We do add the hydrogen, but the hydrogen in this first step definitely goes to the oxygen. And the reason for that really is because if you remember the carbon oxygen double bond, that's actually more negative. This is more positive. And what we're adding here is actually like an H plus. So the plus is attracted to the negative, so it ends up there. What we're left with on the other side is something that's really negative charged. And that negative is actually attracted to the positive side of the carbon. And that's how come that guy sort of ends up, over there. So the oxygen part that has the carbon attached will actually go to the carbon. So a good way to remember that is the part that has the carbon goes to the carbon. The part that's just the hydrogen will go to the oxygen. And when we do that, what we end up with up here to the right is, again, our hydrogen will attach over there. And on the bottom, we'll attach this oxygen carbon group, which is really the other part of the alcohol. So again, just the kind of color code here. This guy goes here. And what do we use there? Green. Looks like that green. I think this guy ends up there. Now, what we have actually produced here actually has a special name, and this is what is referred to as a hemiacetal. You can kind of think of hemi as something that has OH in it. Acetal because it really comes from an aldehyde, and this is what is known as a hemiacetal. So what are the major parts of the hemiacetal? Well, you want to look at where the carbon-oxygen double bond was, and you want to look at that carbon, and it typically will have sort of 3 things attached to that carbon. It will definitely have an OH group, which is what we see here. It will have an oxygen carbon group, so like an oxygen with carbon attached, which is what's on the bottom, and it will have a hydrogen. So those 3 things there, especially the OH group, is what makes this thing a hemiacetal. OH group attached to that carbon where the double bond used to be, and hydrogen, because it really did come from an aldehyde, so that hydrogen hangs out there, and this oxygen carbon group. And you questions on that there? Now, this is what you get when you add just one alcohol to an aldehyde. If you happen to add two alcohols to the aldehyde, the first thing that would happen would be you would make this hemiacetal. And then what would happen is that alcohol then would add to this hemiacetal. So let's take a look at what happens when we add in a second alcohol. And it could technically be the same alcohol, could technically be a different alcohol, but we'll use the same alcohol here. So we're going to take this hemiacetal that we made in the first step, and we're going to add another alcohol, and I'm just going to draw it like this, and we'll do the same alcohol in this case. Okay. So what's going to happen in this case, though, is we've kind of already added some stuff. So actually what we get is we will actually get water to be formed. And water is going to come from basically the OH that's here and the H that's here. So these two guys are going to come together basically to make water. So what does that mean? Well, it means that we have basically taken out OH from our structure on the left. And that means we could redraw it. I'm just going to kind of redraw it on the bottom here. CH3, CH2, C, H, and this guy here. Now, we kind of have a hole here where that kind of OH came out of. And what's going to fill that spot is what is left on the alcohol. So if we look at our alcohol, we didn't put it anywhere. We didn't put these guy anywhere. So this guy, which again is like an oxygen carbon group, will find its way pretty much over here. Pre-color it there. And we will get this connection of this oxygen carbon group happening here. And this is what we get when we do a two alcohols. Fix this up here, kind of butchered writing it. Let's try this one more time. CH2, CH2, CH3. There we go. And highlighting right there. This, when we add actually two alcohols total to an aldehyde, we get what is referred to now as an acetal. So the hemiacetal has an OH group. The acetal does not have an OH group. And again, what makes up an acetal is if we look at where that carbon oxygen double bond used to be, we have in this case two oxygen carbon groups. So that is an oxygen carbon group, an oxygen carbon group that really come from the alcohols. And we have a hydrogen, which is right here. So this is the end result of adding basically two alcohols to an aldehyde. Will take you all the way down to what's known as an acetal. You have the two oxygen carbon groups and the hydrogen. If you add just one alcohol to a aldehyde, you end up with the guy in the top right corner, which is known as a hemiacetal. And again, you can think of hemi as like there's got to be an OH group there. And we have an OH group, a hydrogen, and just one oxygen carbon group. Any questions on those reactions there? Now, ketones actually do pretty much an identical set of reactions, I guess is what I'm trying to spit out there. So let's take a look at what happens when this sort of process occurs with a ketone. So let's take a ketone here. We'll just take a nice simple ketone maybe, so less to draw. There we go. But it doesn't really matter if there's more carbons or, there wouldn't be less carbons, but if there's more carbons. It really does work the same way. So we're going to take our ketone and we're going to add an alcohol to it. And again, we're just going to maybe take a simple alcohol here, like methanol. And the first step here is pretty much identical to what we just talked about. Again, it's all going to happen right here. We're going to make that into a single bond. So CH3, CH3, and now we're going to single bond this guy. And the purpose of that is so our alcohol can add, and our alcohol will add exactly like it did with the aldehyde. It's going to add an H, and it will add that oxygen carbon part of it, which will go with this here. So just like before, the hydrogen is actually going to be attracted to the oxygen because it's kind of positive. Oxygen is kind of negative. This oxygen carbon group, which is technically negative, is attracted to the positive carbon there. And what that will end up giving us again is a hydrogen up there on the oxygen, making an OH group, and our oxygen carbon group here will add. And again, just to color code it there, we ended up with this here and our hydrogen over here. And this also has a special name, although some people will still call this a hemiacetal. Some people will also call this a hemiketal because it comes from a ketone. So hemiketal, and again, some books will just simply call it a hemiacetal as well. It has kind of the same components as a hemiacetal. It has, again, an OH group, which is here. It has an oxygen carbon group, which is on the bottom. And the one thing that it does not have, and how we know it actually comes when we look at this carbon, how we know it actually does come from a ketone rather than an aldehyde, is there's no hydrogen there. So there's no hydrogen on that carbon. Just to give you a reference point, if we go back to our hemiacetal, there is a hydrogen there because it came from the aldehyde that you started with. So if you see a hydrogen in this sort of hemiacetal, you know you started with an aldehyde because that hydrogen carries across. We do not see that in the ketone because when we look at our ketone, we did not start with a hydrogen there. So we do not end up with a hydrogen here. So that's a main difference between those two. Any questions on that there? Now, this again is what you would get if you just added one alcohol here to the ketone. And again, hemi, you see the OH there. If we added two alcohols to this ketone, this reaction would continue on. So I'm just going to redraw our hemiketal here. And we'll add, in this case, again, it could be a different alcohol, but we'll just add the same alcohol. And again, the exact same thing happens as it did in the hemiacetal. Is at this point, we're going to make water. And the water is going to come from the exact same spot. It's going to come from this OH. It's going to come from this H. They're going to come together here to make the water. And just like it did before, when we do that, that pretty much takes the OH off of our hemiketal, and we could redraw it without that OH. And by removing that OH group, it also makes room here on the carbon for the other part of the alcohol to now come in and basically take its place. So now this guy has, again, a spot over here to come in. And if we do, we will see the OCH3 come in here. And this guy, which is starting with a ketone that you added not one, but two alcohols to, ends up with what is known as a ketal, just like the other one is referred to as an acetal. Acetal A coming from an aldehyde, ketal K coming from a ketone. And what this guy has is, again, very similar to what we see in an acetal. It has two oxygen carbon groups, which is this group and this group. And again, just like we see up here, it has no hydrogen on this carbon. And again, that is different than the acetal, which again still has the hydrogen that's present. Here, the ketal does not. So addition of one alcohol to a ketone gets you a hemiketal, which has an OH group, oxygen carbon group that actually comes from the alcohol and does not have a hydrogen. If you add two alcohols, takes you all the way down to a ketal where two oxygen carbon groups and no hydrogen attached there. Any questions on these reactions here? Okay, so I just wanted to kind of go over these couple of reactions here and sort of what we get. That way you're